All right, so I want to take some time going over the chapters 1 and 2 test in detail. I'm going to go over every single problem and hopefully go over any questions that you might have. And if there are any additional questions you have, you can come and see me with those questions. So I'm going to start with the chapter 1 test. Number 1 gives you 2 points, A, B, and asks you to find the length of AB and the coordinates of the midpoint. So let me go ahead and plot that segment AB. There's A, -2, -6, and then B is at -4, 2. Okay, so that's the segment AB. I'm going to go ahead and connect the dots. Do that here. All right, so there's my segment AB. So to find the length of it, you can use the distance formula. So remember, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So you can use that to find your distance from A to B. If you label the 2 points x1, y1 and x2, y2, you can get what that is. So let me go ahead and figure out what that is. So basically subtracting the x's, so that would be -2 minus -4, or whatever order you do it, squared, plus subtracting the y's, -6 minus 2 squared. That would be the square root of -2 plus 4 is 2 squared, plus -6 minus 2 is -8 squared. 2 squared is 4, -8 squared is 64, so that's the square root of 68. Now we do want to simplify that as much as possible. So when I think of the square root of 68, you can break that into 4 and 17. So that would be 2 root 17 for the length of AB. And we're not going to use a calculator for really any of this. So I just want to keep it kind of how it is, just like that, in exact form. Part B asks for the midpoint. The midpoint formula is really just an average. x1 plus x2 over 2, comma y1 plus y2 over 2. Okay, it's just an average of the x's and an average of the y's. So that would be -2 plus -4 over 2, comma, -6 plus 2 over 2. Which would be -6 over 2 is -3. -6 plus 2 again is -4. Over 2 would be -2. So -3, -2 would be that midpoint. That's always good to plot that. Just make sure it looks like a midpoint. 1, 2, 3, 1, 2. Yeah, that looks like a midpoint. Okay, so I can get it that way. Number 2 asks you to find the value of A if the point 4, -2 is on that given line. Let's go ahead and do that. All right, so we're looking at the line 2x plus ay equals 14. And I want to check, or I want to find the value of A if 4, -2 is on that line. So plug in the point. Plug in x equals 4 and y equals -2. And we can solve for A from there, because if that point is on the line, it should satisfy that equation. So 2 times 4 plus A times -2 equals 14. That's 8 minus 2A equals 14. If I subtract the 8 over, -2A equals 6. Divide by -2 means A is -3. All right, for number 3, so solve these equations simultaneously, then sketch graphs of the lines and label the intersection point. So this is a system of equations. 2x plus 3y equals 2. The second one is 6x minus y equals -4. All right, so to solve the system of equations, there are a litany of ways you can do that. The way that I'm going to do is elimination or combination, depending on what you were taught, where basically you multiply one or both of the equations by something, add them together to make one of the variables disappear. So I'm going to multiply the bottom equation by 3 on both sides, because that'll make the y's cancel. 2x plus 3y equals 2. 18x minus 3y equals negative 12. And I can add those straight down. So when I do that, 2x plus 18x is 20x. The 3y and negative 3y cancel. And 2 minus 12 is negative 10. And notice the y's went away, so now I can just solve for x, single variable. So if I divide by 20, negative 10 20ths is negative a half. And then I can substitute that into any equation from earlier to solve for y. So let's say that I substitute it into this one right here that I'm circling in green. So what does that give me? 2 times negative a half plus 3y equals 2. 2 times negative a half is negative 1, plus 3y equals 2. Add the 1, 3y equals 3, divide by 3, and y equals 1. So if we write that as an ordered pair, the solution to the system is negative 1/2, 1. Now the problem also asks you to graph this and label the intersection point. So remember graphically what this looks like. If I go ahead and get a graph here, graphically what this is going to look like is 2 lines, because this is a linear system of equations. It's going to look like 2 lines that intersect at that point negative 1/2, 1. Now to graph these lines, you could put them in y equals mx plus b in slope-intercept form. You could just plot using intercepts. That's what I'm going to do. So to plot using intercepts, remember when you plug in 0 for x, you get the y-intercept and vice versa. So by that logic, I get that the y-intercept is at about 2/3. Oh, my graph got a little screwed up here. Let's try that again. My y-intercept is at about 2/3. Try and recenter this. Looks a little better this time. Okay. So I have a y-intercept at 2/3. Maybe about right there. And we've got an x-intercept that looks like at 1. And so if I try and put a line through that, it's not going to be perfect. If I put a line through that, it might look something like that. That's kind of what the first line looks like. The second line, again, if I just kind of use that original equation and plot using intercepts, looks like the x-intercept is at negative 2/3. Plot this one in red. Negative 2/3. And it looks like the y-intercept is at 4. So if I get a straight edge and I put those together, let's see what I get. I get that line. Something kind of like that. And sure enough, if I look at the intersection point, it's not perfect because I didn't quite get the 2/3 probably correct. But it intersects about right there, which looks like about negative 1/2, 1, as it should. Okay, so you can kind of use that to verify your answer. Number 4 asks for the slope and the y-intercept of that line. 4x minus 2y equals 7. The easiest way to do this is just put it in slope-intercept form, right? Y equals mx plus b is the slope-intercept form of a line. So negative 2y equals negative 4x plus 7. Divide by negative 2. Y equals 2x minus 7/2. Compare that to the slope-intercept form, y equals mx plus b. And you can see that the slope is 2. The y-intercept is negative 1/2. Sorry, not negative 1/2, negative 7/2. So that's the slope and y-intercept of that line. Just put it in slope-intercept form, and that should do it. All right, 5, more stuff about lines. Lines will be very important, believe it or not. They seem like a very simple concept, but we'll be using them a lot in here, and honestly a lot in calculus next year as well. So tell which of the following equations have parallel line graphs and which are perpendicular. Again, the easiest way to do this is to look at the slopes of each of these. So I'm going to put each of these in slope-intercept form if they're not already, and just compare the slopes. Because remember, parallel lines have the same slope, perpendicular lines have opposite reciprocal slopes. So notice B is already in slope-intercept form, so I don't need to change anything. I already know that for B, the slope is equal to 3/2. That's already good to go. These other ones, I need to put them in slope-intercept form, so let's move some stuff around. 3y equals negative 2x plus 1. Divide by 3, and I get y equals negative 2/3 x plus 1/3. So notice in this case, when I put it in slope-intercept form, the slope here is negative 2/3. All right, let's check out C. If I get this solved for y, negative 4y equals negative 6x plus 10, just solving for y. Y equals 3/2 x minus, honestly, who cares, but we'll say 5/2 because we really just care about the slope. So in this case, the slope is 3/2. Okay, so let's put everything together here and say, okay, which of these are parallel to each other, which of these are perpendicular? Well, notice that B and C have the same slope. So I know that line B, is in black, I know that line B is going to be parallel to line C because they have the same slope. Notice that A and B have opposite reciprocal slopes, negative 2/3 and 3/2. So I know that A is perpendicular to B, and also A and C have opposite reciprocal slopes. So A is also perpendicular to C. Okay, so that's a way of looking at it. Just look at the slopes. That's all you need to do. It's a lot easier than trying to graph them and just investigate it that way. All right, 6 is asking for the equation of a line through 2 points. This is always a good skill to have. So 6, negative 2, and negative 3, 1. So the easiest way to do this is to use what's called the point-slope form of a line. This will be extremely important in calculus, even this year from time to time. Point-slope form of a line is y minus y1 equals m times x minus x1. M is your slope, and x1 and y1 is any point that the line passes through. So my slope, remember the slope formula, y2 minus y1 over x2 minus x1 from algebra. If I just label these arbitrarily, x1, y1, x2, y2, that would be 1 minus negative 2 over negative 3 minus 6, which is 3 over negative 9, which is negative 1/3. So the slope is negative 1/3. And then where it says x1, y1, I don't have to put what I labeled as x1 and y1. I could even put x2 and y2, or really any other point that's on the line, that I know is on the line. I'll go ahead and put x1 and y1 just because that's what I labeled it as, and ultimately it doesn't matter. But you can also put the x2, y2 there and it works. So if I plug this in the point slope form, y minus y1 equals m times x minus x1. Now, notice it just said to write an equation of the line. It gave no indication how it wants you to write it. So I'm just going to leave it like that. I'm going to leave it in point slope form because it didn't tell me I had to do anything with it. Sure, I could change that minus to a plus. Sure, I could distribute the negative 1/3. Sure, I could put it in y equals mx plus b, or I could even put it in standard form. But it doesn't care how I put it, so why don't I just stop here before I maybe make an algebra mistake? So if it doesn't specify what form it needs to be in, I'd say absolutely leave it in the simplest form you can. And by simplest, I mean the simplest for you, right? Do the least amount of work possible. And this is something you'll do in calculus as well. All right, 7, kind of similar. Write an equation of the line that passes through 5, 5 and is parallel to 4x plus 3y equals negative 2. All right, so remember, parallel means same slope. So let's start by finding the slope of that line they gave us. So if I have that and I want to find the slope, just like we were doing in a lot of the previous problems, I can solve for y. I that by 3, so that would be negative 4/3 x minus 2/3. So that line has a slope of negative 4/3. So if that line has a slope of negative 4/3, and I want a parallel line, I want another line with a slope of negative 4/3 because I want the same slope. So look, I want that slope, I want that point. It'd be really helpful if there were some form of a line that we can use if we have a point and a slope. And we do, right? The point slope form of a line from the last problem. Y minus y1 equals mx minus x1. And again, I'm just going to leave it like that. Sure, you can change it to something else if you want, but I'm going to keep it simple on myself and just leave it like that. So parallel means same slope. Remember, perpendicular means opposite reciprocal slope. All right, write an equation of a line with an x-intercept of negative 3 and a y-intercept of negative 5. Well, writing those as points, an x-intercept of negative 3 would be negative 3 comma 0, because it lies on the x-axis. There is no vertical component. And conversely, a y-intercept of negative 5 means it's the point 0 comma negative 5. There is no x component to it. It just lies on the y-axis. So this is just like number 6. Just get an equation of the line through it, and we're good to go. The slope would be y2 minus y1 over x2 minus x1. Negative 5 over 3. Negative 5/3 would be my slope. And then I could write it a few different ways. I'll be a little bit different this time, because we know another form of a line we can use is the slope-intercept form, y equals mx plus b, and that's we can only use if we have a slope and a y-intercept. And in this case, we do. We have a slope right here. We have a y-intercept right there, negative 5. So I can go ahead and write it that way. Y equals negative 5/3 x plus b minus 5. Do I have to write it that way? Of course not. You can write it in point-slope form if that makes you happy, or standard form if you just like to make things unnecessarily difficult. But that's a way that you can write that using something different than the point-slope form. Just be comfortable with any of it. All right, number 9 says to write an equation of the vertical line through 4, negative 2. All right, I'm not going to draw a very official picture here. But if I'm drawing a vertical line through 4, negative 2, 4, negative 2 is somewhere down here. Remember, vertical means straight up and down, so something like that. We want to write an equation that describes that. So notice that that line, that vertical line that goes through 4, negative 2, every single point on that line has an x value of 4. 4, 6, I don't know, 4, negative 2. 4, negative 30, right? You know, something like that. Those all have an x value of 4. So the way we describe that line is it's the set of all points where x equals 4. If you ever get confused about, oh man, is it x equals or y equals for a vertical line? Just ask yourself, are all the points on that sharing the same x, or are they sharing the same y? And that's the way you can write it. So vertical lines are just x equals a number, namely the x value of that point that it passes through. Okay, erase that to give myself more room. 10, the geometry question. Describe the steps of finding the equation of a perpendicular bisector of a line segment. I'm not going to write those out explicitly, but I am going to talk about the steps as I do this problem. So give me a sec to pause, and I'm going to go ahead and try to graph this so you don't have to watch me do that. All right, so I've graphed number 10 here. That's the segment that they gave us. I'm going to find the perpendicular bisector. So a perpendicular bisector, if you think of the words in that, first of all, perpendicular means we're looking for something that is perpendicular to that segment. So the first thing I'm going to do is I'm going to find the slope of the segment and then get its perpendicular slope from there. So the slope of the actual segment, I'll just call it m. You know, that's just rise over run. I could just count the boxes if I want. Notice from that top left point to the bottom right one, I'm going down 1, 2, 3, 4, 5, 6, 7, 8, down 8, and right 1, 2, 3, 4, 5, 6. So down 8, right 6 would be negative 8 over 6. or negative 4/3. So that's the slope of the actual segment. You can use the slope formula as well if you want. But the perpendicular slope, that's what I'm really looking for. I have to change the sign and flip it, right? Opposite reciprocal. So I'm going to say m perpendicular with that little perpendicular symbol would be 3/4. So the perpendicular slope is going to be 3/4. So I found my perpendicular slope. I've got that part. The second part of it asks for a bisector. If you remember from geometry, bisect means to cut in two. Think of the parts of the word. Bi meaning two, sect meaning cut. So it cuts it in two. In other words, it goes to the midpoint. So I'm looking for a perpendicular line that goes through the midpoint of that segment. So we find the perpendicular slope, we find the midpoint. I'm going to call that B, I guess. Or I'll call it C in case you called the segment AB. So that midpoint, again, is the average of the x's and the average of the y's. We did this earlier on number 1b. So average of the x's, 7 plus 1 over 2. Average of the y's, 0 plus 8 over 2. Would be 8 over 2 is 4, 8 over 2 is 4, so that's the midpoint. Again, let's just plot that, make sure it looks like a midpoint. 1, 2, 3, 4, 1, 2, 3, 4. Yeah, that looks like a midpoint, so we're good. So what's the last thing we need to do? Well, we just need to say we have the slope, we have the point, so we can use the point slope form of the line to write the equation. So use point slope to write the equation. Okay, so let's do that. Y minus y1 equals mx minus x1. There we go. It doesn't ask for it to be in any particular form, so that works just fine. Passes through the midpoint, that's my x1, y1. And the slope of that perpendicular bisector is 3/4. If you went ahead and graphed that, you would see that it's perpendicular to the line, to the blue segment, and it goes to the midpoint, which is what we're looking for. All right, so the number 11's kind of a linear word problem here. Says a teacher must grade 23 exam papers, working for 63 minutes. She can grade 7, and we want to figure out how long it's going to take her to grade all 23. So it says give an equation of the linear function that models the number of exams as a function of time. We'll notice that it also passes through 0, 0. It makes sense that if she hasn't worked at all, she hasn't graded any exam. So it passes through 0, 0, and 63, 7. So let's find the equation of the line through that. The slope would be 7 minus 0 over 63 minus 0, which is 1/9. The y-intercept is 0, so I can just use y equals mx plus b. I'm going to write this as a function, though, so I'm going to, instead of saying y, I'm going to say f of t, because my independent variable is going to be t for time. Okay, so I'm going to say f of t equals mx plus b, 1/9 t plus 0. You could write that as y equals 1/9 x, that'd be just fine, but I'm going to write it as a function because it mentioned it was a function. All right, so it says use the equation to find approximately how long it'll take to grade all the exams. So here you have to be a little careful. How long to grade. It says 23 exams. That looks like 23 exams. So notice it says how long is the question, which means we're solving for t, given that f of t is 23. Right, f of t is the number of exams graded after t minutes. So I'm going to say, all right, well, f of t is 23 equals 1/9 t. I can multiply both sides by 9. T equals 9 times 23. So you can multiply that out. 9 times 23 is 207 minutes. If we want to put that in a more reasonable time, I could divide that by 60. say, well, it goes in 3.45 hours. That's also not a very reasonable time measurement. If I want to change that into hours and minutes, I can take the 0.45 and multiply by 60. That'll give me the number of minutes that is in an hour. So let's do 60 times 0.45 would be 27 minutes. So I can say, okay, altogether this is 3 hours, 27 minutes. That's a more reasonable way of expressing that time. If you were taking a test and your teacher said you have 3.45 hours, it'd be a little harder to think about exactly how much that is. But 3 hours, 27 minutes, that's an easier way to write it. All right, so for the second half of this Chapter 1 test, it's doing a lot of stuff with complex numbers and with quadratics. So let's take a look at that. So it says express each complex number in the form a plus bi. So square root of negative 50 minus square root of negative 8. So remember, if you have a negative under a square root, that can get pulled out as the imaginary number I. So I root 50 minus I root 8. Pull those out as the imaginary number I. Remember, I is the square root of negative 1. And then we can simplify these roots and hopefully put these together. Square root of 50 is 5 root 2. So this would be 5I root 2 if I multiply by the I that's already there. Square root of 8 is 2 root 2, so minus 2I root 2. And these are like terms. They both end in an I root 2. 5I root 2 minus 2I root 2 is 3I root 2. Or if you want to write it in the form a plus bi, 0 plus 3 root 2I. That's how you could write it in that form. 13, 2 plus 3i quantity squared. I hope that you know from Algebra 2, hopefully had it said to you many times, that you cannot distribute a squared, so you can't just say that's 2 squared plus 3i squared. Instead, when you're squaring something, you're multiplying it by itself. So we're going to multiply this binomial by itself. Use the FOIL method to do that, if that's what you're comfortable doing. 2 times 2 is 4, plus 6i is plus 12i, plus 9i squared. Just foiling that out. Remember that since I is the square root of negative 1, you square both sides, we know that I squared is negative 1. That's an important fact. So this becomes 4 plus 12i minus 9 for multiplying by negative 1. 4 minus 9 is negative 5. So negative 5 plus 12i would be that result. All right, 14 is dividing complex numbers. 1 over 2 plus 3i. Remember, when you're dividing complex numbers, we multiply and divide by the complex conjugate. So the conjugate just changes that sign on the imaginary unit. So we're going to multiply and divide by 2 minus 3i. And, people often wonder, why do we do this? Well, it's because in the denominator, it creates a difference of 2 squares where the imaginary unit disappears. We'll see that in a second. So in the numerator, 1 times 2 minus 3i is just 2 minus 3i. The denominator, if I FOIL that out, kind of like the last one, that'd be 4 minus 6i plus 6i minus 9i squared. Numerator, there's nothing we can do with at the moment, 2 minus 3i. The denominator, yes, the negative 6i and the positive 6i cancel. And again, we know that I squared is negative 1, so that becomes 4 plus 9 on the bottom. 2 minus 3i all over 13. And you can break that up into 2 separate fractions, 2/13 minus 3/13 I. That way it is in that standard form, a plus bi, that it needs to be in. In general, if we have a complex number, we want to write it in that standard form, okay, if it has a real and an imaginary part. So we multiply and divide by the complex conjugate when we are dividing complex numbers, which is what we're going to see in number 15 as well. All right, multiply and divide by the complex conjugate of the denominator. That way we don't have any imaginary units in the denominator. Anytime you multiply a complex number by its conjugate, you always get a positive real number, a non-negative real number. Okay, that'll always be the case. So that's going to get rid of the imaginary unit in the denominator. So FOIL in the top, root 3 times root 3 is 3. Plus I root 3 plus I root 3 is plus 2I root 3 plus I squared. The denominator is going to look similar. Root 3, FOIL it out, plus I root 3 minus I root 3 minus I squared. Notice in the denominator the I root 3's cancel, which is exactly what we wanted. Don't forget that I squared is negative 1. So in the numerator to have 3 plus negative 1, that's 2, plus 2I root 3. And the denominator, again, I squared is negative 1, so 3 minus negative 1 is 3 plus 1, which is 4. And again, I'm going to split this into two separate fractions with the real and the imaginary part separate. So 2/4 plus 2 root 3 over 4I, right? A plus BI. If I simplify those fractions, that'd be 1/2 plus root 3 over 2I. Okay, so just like the last one, it's just the numerator also had some imaginary stuff in it, but we ended up with a result very similar to what we had on number 14. All right, 16 is actually a little bit more straightforward. 4 times 3 plus 2I minus 5 times 1 minus I. Basically just treat I like it's a variable and you're just simplifying a variable expression. 4 times 3 is 12 plus 8I if I distribute that through, minus 5 plus 5I. And then just gather your like terms. 12 minus 5 is 7. 8I plus 5I is 13I, and there is your complex number. For number 17, we have a power of I to the 17th. Now what I like to do for this is I like to sort of think of it as a pattern. So if you have I to the 0, that's equal to 1. Actually, I'll start with I to the first. I to the first is equal to the square root of negative 1. I squared is equal to negative 1, because you can get that from squaring both sides. If I multiply both sides by I get I cubed is negative I, and I to the 4th would end up just being 1. And then the pattern repeats after that. Okay, the pattern repeats after that. I to the 5th goes back up. You have 5, 6, 7, 8, and then it repeats back 9, 10, 11, 12. Okay, so if we have I to the 17th, I can kind of count that and say, okay, I to the 17th, that's very close to I to the 16th. I'm going to say that's I times I to the 16th. I to the 16th is a multiple of 4, so it's going to line up with 1 right there, because it repeats. 4, I to the 4th, I to the 8th, I to the 12th, I to the 16th. Those will all be 1 because it repeats. Powers of I repeat after that. So I times 1 would just be I. Or if you want to write it in the standard form for a complex number, 0 plus 1I if you really want to, or just 0 plus I. There's a lot of different ways you could write it. So knowing those powers of I is something you hopefully learn in Algebra 2. All right, 18 is moving on to something a little different. Now we are solving quadratic equations. Something a little bit harder than doing it with linear equations, but it's something you need to be extremely comfortable with as you encounter them this year, and you will see a lot of quadratic equations. Quadratic equation is when you have an x squared in your equation that you're trying to solve. In general, you have ax squared plus bx plus c equals 0. And to solve this, there's a multitude of ways you can do it, but in general, you want everything on one side. So I'm going to subtract the 5x over. You want everything on one side, and you want to try and factor it if you can. Okay, if you can't, we'll talk about what to do later. For this one, you should be able to factor it. So to factor this, you can use the guess and check method, say, okay, well, remember the first two have to multiply to 7x squared, so I'm thinking 7x, and x is about my only possibility. The last two need to multiply to -2. So what if I try 2 and 1? And then I don't put signs on it just yet. I kind of foil it out in my head and see if it could potentially work out that that middle term is a -5x. So let's try it. 7x times x is 7x squared. That's good. 7x times 1 is 7x, 2x. Okay, is there a way I can combine 7x and 2x to get -5x? Yes, there is. I could put a negative here and a positive there. That would be -7x plus 2x is a -5x. So that's what I want. And then just check the last one and make sure. +2 times -1, yep, that's -2. So we're good. So we moved everything to one side, we factored it, and then remember we set each factor equal to 0 and solve for x. So this would be x equals -2/7, x equals 1. And I'm not picky about the way you write it. You can just put a box around each answer, or put x equals and then put them all next to just 1 x equals. It doesn't matter. As long as I can easily tell what your solutions are, it should be fine. Part B is another quadratic equation, x squared minus 4x equals 9. Again, for a quadratic, it's best to move everything to one side and try and factor it. I'm going to go ahead and tell you now, though, if you try and move the -9 to the other side and factor it, it is not going to factor. This will not factor if you try and do that. So if it doesn't factor, you have a couple options. You can do the quadratic formula, or you can complete the square. I'm going to opt for completing the square here because it actually works out pretty nice, and we are going to be completing the square at various times throughout this year, and it's good to know. So remember, for completing the square, you put the variables on one side, the number on the other, and we're going to add a mystery number to both sides that's going to make the left side become a perfect square trinomial. If you remember from Algebra 2, that magic number you're looking for is half of that circled number squared. Half of it squared. So half of -4 is -2. -2 squared is +4. So that's what we're going to add to both sides. So you look at the number in front of the x, you half it, and you square it, and add it to both sides. Now on the left side, you can check. This is going to factor to x minus 2 squared. It's always going to end up being x and then half of that circled number squared, including its sign. You can check, but it will always factor to a perfect square trinomial if you did everything right. So x minus 2 squared equals 9 plus 4 is 13. Now that we have the squared quantity isolated and the number on the other side, we can square root both sides. Remembering that when you square root both sides, you need a plus or minus on the other side. So plus or minus root 13. Or an absolute value or whatever, which is going to turn it to a plus or minus. So now I just isolate the x. X equals 2 plus or minus root 13. And we'll leave it like that. We won't worry about a decimal. Could you use the quadratic formula for that? Absolutely. But I did completing the square because it's something we're going to have to do with conics later this year, and a couple other things. So it's good to know how to complete the square. All right, one more quadratic equation for now. Part C, x squared plus 2x plus 2 equals 0. I will tell you right now you cannot factor that. So it is already moved to one side, but you cannot factor it. So don't bother. I will do the quadratic formula this time, which you do want to have memorized. You never know when that might pop up. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula. A is the number in front of the x squared, b is the number in front of the x, c is the number, the constant basically, the number with no x. Learn that in Algebra 2, hopefully before that as well. So if I plug all that in, x equals -2 plus or minus the square root of 2 squared minus 4 times 1 times 2 all over, clean that up a little bit, all over 2a, 2 times 1. If I clean this up, -2 plus or minus the square root of 4 minus 8 is -4. all over 2. We recalled earlier that the square root of a negative, you can pull out the negative as an I. So that would be I times the square root of 4, or 2I, over 2. I'm going to rewrite this so I have more room. So negative 2 plus or minus 2I over 2. And I'm always careful about canceling with the top and bottom. You can only cancel on the top and bottom if there's a GCF you can cancel on the top and bottom. So notice in the top I can pull out a 2 as a greatest common factor. And then that 2 that I pulled out as a greatest common factor is something I can cancel. When you're canceling top and bottom, make sure it's a GCF before you cancel. Okay, pull out that GCF first and then cancel. So negative 1 plus or minus I would be your 2 solutions to that equation. So they're imaginary solution. All right, so number 19 is asking us to use the discriminant to solve this equation, and that'll kind of inform what method we should use to solve it. So when you're looking at a quadratic equation, the discriminant is that quantity that's under the square root in the quadratic formula, b squared minus 4ac. That's the discriminant. So in this case, the discriminant would be negative 2 squared minus 4ac. That's 4 minus 24, which is negative 20. So there's a couple things that tells us. First of all, if your discriminant is negative, that tells you that there are 2 complex conjugate solutions, 2 imaginary solutions that are complex conjugates of each other. It also, we notice that that is not a perfect square. If the discriminant is a perfect square, it's something you can solve by factoring. If it's not a perfect square, it means that you have irrational solutions. And so I either have to use the quadratic formula or I need to use completing the square. Well, the fact that I already found the discriminant will make the quadratic formula a lot easier. So that's how I'm going to solve it. I'm going to solve it using the quadratic formula. X equals negative b plus or minus, well, I already know what the discriminant is. B squared minus 4ac, that was negative 20, all over 2a would be 2 plus or minus, so the negative comes out as an I. Square root of 20 is 2 root 5, so 2I root 5 over 6. Again, before I kind of cancel, I want to take out a GCF first, so take out the GCF 2 in the top, 1 plus or minus I root 5 over 6. Now that I've taken out the GCF, now I can cancel that 2 with the 3 down there, or make that a 3 down there. So I get 1 plus or minus I root 5 over 3. Or if you wanted, you could write that in standard form, kind of like 18c was. But that's the way that I'm going to write it because that's the way the book did it. So using the discriminant kind of sometimes helps you inform which method is best. Again, if the discriminant is a perfect square, you can factor it. If the discriminant is negative, you're going to expect 2 complex conjugate solutions. All right, for 20, we're going to be graphing a couple quadratics. So starting with y equals 8 minus 2x minus 1 squared. If you rewrite this with the 8 at the end, this is in the vertex form for a parabola. So from Algebra 2, the vertex form of a parabola, and there's a few different ways of writing it, is y equals ax minus h squared plus k, where h comma k is your vertex, a is your stretch factor or shrink factor, and then the x and y just kind of hang out in the equation. Remember, if a is positive, it's going to open up. If a is negative, it's going to open down. So if I sketch a graph of this, not quite sure exactly how much room I'll need. Should probably make it decently big just in case. Maybe something like this. All right, so looking at this equation up here, notice h comma k, the vertex would be at 1 comma 8. That's the h and the k value, so 1 comma 8. Perfect. And because a is negative, it's going to open down. Now remember, traditionally, if a is 1 or negative 1, you're just going to go like left 1 and down 1 and left 1 or right 1 and down 1. So something, it would usually be like right there. But our vertical stretch factor is 2. So instead of doing that, see if I can erase these. That erased the whole graph. Okay, there we go. Instead of doing that, I'm going to go, when I go left and right, I'm going to go up and down, or whatever the case is, whatever the vertical stretch is. So if this is a negative, I'm going to be going down. Since a is 2, I'm going to go left 1, down 2, right 1, down 2. Okay, kind of like that. If you wanted to get more, you could then plug in some x values to get more, but I think this will be a fine way to get what this is. If I really wanted to know where it hit the x-axis, I could plug in 0 for y and solve for x. I think this will be an okay way of doing it just for now. Do a really sloppy parabola through these. 3 points will be okay for now, and I'll let you know if and when you need more. So that's what the graph of 20a would look like. 20b is in a different form. It is in standard form, x squared minus 6x plus 5. When it's not in that vertex form, you can use the vertex formula to find the vertex. The vertex formula is x equals negative b over 2a. That gives you the x value of the vertex. You'll prove why that's the vertex formula in calculus, although you can kind of look at the quadratic formula to see why it is. We may talk about that in class later. Negative b over 2a would be negative negative 6, that's 6, over 2 times 1 is 2, so x would equal 3. That's the x value of the vertex. But as you know, a vertex is a point, so it also needs a y value. So to get the y value of the vertex, just plug it back in. 3 squared minus 6 times 3 plus 5. That's 9 minus 18, which is negative 9, plus 5 is negative 4. So the vertex is at 3, negative 4. So if I make a little graph over here, just say something like this. Hopefully this will be decently big enough. 3, negative 4. What I do if it's in this form, if it's not in that vertex form, is I plot the vertex. I notice that a, the value in front of the x squared, is positive, so I expect this to open up. And I just plot a couple points on either side by just plugging in x values. So first of all, you notice, okay, the vertex is at x equals 3. What if I plug in x equals 2? So I'm kind of making like an xy table. What if I plug in x equals 2? What does that give me? Well, if I plug in x equals 2 to the original, that'd be 4 minus 12, which is negative 8, plus 5 is negative 3. So 2, negative 3, be right there. If I plug in something like 1, plug in 1, I would get 1 minus 6 is negative 5, plus 5 is 0. So 1 is a 0. Let's get that. And then I can actually use symmetry and say, well, we know there's an axis of symmetry at that vertex. I didn't do the axis of symmetry on the last one, but that's your axis of symmetry, that vertical line that goes through the vertex. And so it should be the same on the other side. So we should have 4, comma, negative 3, and 5, comma, 0. So this one you can get kind of a nice 5-point graph of this. It's going to look something like that. And so it says label the vertex. There's our vertex. The axis of symmetry is right there at x equals 3. Excuse me. The intercepts, notice it hits the x-axis at 1, comma, 0, and at 1, 2, 3, 4, 5, comma, 0. And if I wanted to get the y-intercept, that's really easy. The y-intercept you just get by plugging in 0 for x. And I didn't do this perfectly, but the y-intercept should be at 0, comma, 5. Those are kind of the most critical parts to a quadratic function's graph. Okay, 21 asks you to sketch the graph of these two things, a line and a parabola, and find the coordinates of any points of intersection. So let's go ahead and do that. start with the parabola, negative x squared plus 4x plus 1. I'm not going to write out all the work as I graph this because it's very similar to the last one. And then for the line, I'm actually just going to I'll just write it like it is, 2x minus y equals negative 2. So if I sketch a graph of these two, hopefully that will be good enough. The first one is a parabola. You can use negative b over 2a to get what it looks like. That would be negative 4 over negative 2, which would be 2 for the x value. So I'm using the vertex formula. And then to get the y value, I can plug it back in. Be negative 4 plus 8 is 4, plus 1 is 5. Looks like the vertex is at 2, 5. Again, I can kind of plug in a couple points on either side. If I plug in 1, negative 1 plus 4 is 3, plus 1 is 4, so it should be right there. If I plug in 0, I get a y-intercept of 1, and it should be the same thing on the other side. So it's going to look something like that. All right, for the other one, for the line, I'll just plot using intercepts, but you could easily put it in y equals mx plus b if you want. Plugging in 0 for y, I get the x-intercept is negative 1. Plugging in 0 for x, I get the y-intercept is 2. And if I connect the dots, you can maybe see that, maybe, if I can get this to line up, you can maybe see that there is one intersection point. This is what's called a tangent line to this parabola. There's one intersection point. It looks like it's at 1, 4. 1, 4 is the intersection point. Okay, so if you graph carefully, you can do that. Now, what if you didn't graph carefully, or what if it's not a nice number? Well, you'll have to solve this, what's called nonlinear system of equations, where you solve one or both of the equations, or I guess solve one of the equations for one variable and plug it into the other. So for example, what if I solve the second equation for y? I would get y equals 2x plus 2. So substitution is basically the way to do this. Solve that second equation for y, and I plug it back into this one for y. 2x plus 2 equals negative x squared plus 4x plus 1. This is a quadratic equation, so I want everything on one side and 0 on the other. Okay, so if I do that, I get x squared minus 2x plus 1 equals 0. If you factor that, it's actually a perfect square trinomial. It ends up being x minus 1 squared. So when I set that equal to 0, I get x equals 1 with a multiplicity of 2. We'll talk more about multiplicity in the chapter 2 test, but I get x equals 1. And then, with that, we can plug it back in and get the y value, and if you plug it back into either the line or the parabola, you will get y equals 4. So it works out algebraically as well. You need to be comfortable doing either method, graphing or algebraically. You could be asked to do both, in fact. So be comfortable with that and you should be good. All right, last one on the chapter 1 test, number 22. This is a photo processing lab. Lists the following prices for reprints. 29 cents for 3x5, 39 cents for 4x6, 55 cents for 5x7. Find a quadratic function that models the cost in terms of the smaller dimensions. Okay, so basically what it's saying is, if I draw like an XY table, so the smaller dimension of the 3x5 is 3, and the cost is 39 cents, because it says it once in cents, so 3, 39. For the 4x6, the smaller dimension is 4, and that's 55 cents. And for the 5x7, the smaller dimension is 5, and that is 55. Or sorry, wait. I messed it up. 39. Can I move these? 29, 39, 55. Sorry. 29, 39, 55. So it says find a quadratic equation of this form that fits that data. Now, we don't want to use regression here. We want to do this by hand. So the way of doing it is we want to plug each of these points in as x and y and solve for a, b, and c as a system of 3 variables with 3 equations. Okay, so let's plug each of these in for x and y and see what that gives us. Remember, y is the same thing as f of x. So 29 equals a times 3 squared plus b times 3 plus c, if I plug that one in. If I simplify that, I get 9a plus 3b plus c equals 29. And I put the unknowns on the left and the number on the right. I want to kind of put them all in the same form. What if I do the same thing with this one? What if I plug that in for x and y? So that formula that they gave us. Okay, I get 39 for y, a times 4 squared plus b times 4 plus c. That is 16a plus 4b plus c equals 39. Let's do the same thing for the last one. 55 is the y value. A times 5 squared plus b times 5 plus c. That would be 25a plus 5b plus c equals 55. And so what I have right here is a system of 3 equations with 3 unknowns. And last year in Algebra 2, you briefly looked at how to solve something like that. And the easiest way to do it is to do elimination. So pick any 2 of these equations and get rid of any variable. Let's say I look at the first 2 and I subtract them to make the c disappear. So I'm going to subtract those 2, 9a plus 3b plus c equals 29, and subtract the second equation, negative 16a minus 4b minus c equals negative 39. I have to change all the signs because I'm subtracting. If I add those up, negative 7a, or I guess subtract them, minus b, the c's cancel, negative 10. So notice the c's went away there. Let's do that again with another 2. What if I now do that with, let's say, the last 2? What if I do the second equation minus the third one? What's that going to give me? So let's see. Second equation minus the third one. So that's going to give me negative 9a minus b. Again, the c's will cancel. That's the idea. You want to eliminate the same variable you did the first time. Trying to eliminate the same variable with 2 different sets of equations. This would be negative 16. All right, so now look at these 2. Now this is a system of 2 equations with 2 unknowns, and that's really easy to solve. What if I do this first one, I did something like this earlier, minus that second one? So plus 9a plus b equals positive 16. So what if I did that first, that left one minus that right one? That would get rid of the b's. 2a equals 6. A equals 3. So okay, now we know what A is, and so it's just a matter of kind of back substituting to get what B is and then what C is. I have a lot of options here. So what if I take A equals 3, and I don't know, that one looks friendlier to me, so I'll plug it into this one up here, make a nicer looking arrow. Negative 7a minus b equals negative 10. Negative 21 minus b equals negative 10 gives me b equals negative 11, looks like. So now I know A, now I know B. So to get C, I'll plug both of those back into one of the originals. Let's say that I plug it back into this yellow one. So plug in A equals 3 and B equals negative 11 back into that yellow one at the top. 9a plus 3b plus c. 9a plus 3b plus c equals 29. That's 27 minus 33 plus c equals 29. Negative 6 plus c equals 29. And finally, we get c equals 35. So there's my a, b, and c. So when I write my function, f of x equals ax squared plus bx plus c. There's my function that talks about the cost for printing as a function of that lesser print size. All right, and so for part B, it's really easy. It just says, using this model, find the approximate price of a 7:9 print. Well, remember, x is the smaller dimension, so I'm going to plug in x equals 7. In other words, I'm going to find f of 7. See what that is. 3 times 7 squared minus 11 times 7 plus 35. So if I do that, 7 squared is 49 times 3 is 147 minus 77 plus 35. That's going to give me 105. Remember, this is in cents, so that's 105 cents, which means it is equal to $1.05. So that's the Chapter 1 test. And in a minute, we're going to move on to the Chapter 2 test. So looking at the Chapter 2 test, number 1 gives you this polynomial function p of x equals 4x cubed minus 5x minus 2. It asks you to find a few different things using synthetic substitution, or in other words, synthetic division. So the first thing it asks you to find is p of 2. So remember, when you're doing synthetic division, if I want to find p of 2, there's a theorem in your book that tells you that basically the result you get from synthetic division by x minus a is the same thing you would get if you just found p of a, if you just plugged it in. So the thing that you plug in, the thing you get when you plug in a certain value, a, is the same remainder you'll get when you divide by x minus a, whether you use long or synthetic division. So they want us to use synthetic division to do this. So to find p of 2, I'm going to put 2 in my little synthetic division box. And this may look a little different than you did in Algebra 2 last year, but if you remember the way you did it and you like it that way, that's fine. It's basically the same process. We write the coefficients of the polynomial to the right of that, 4x cubed. Notice there is no x squared, so we need a 0 there. Negative 5x, negative 2. All right? So remember the process. You bring down the first number, multiply by the box. 4 times 2 is 8, and then add straight down. 0 plus 8 is 8, and repeat. So multiply by the box. 8 times 2 is 16. Add straight down, that's 11. Multiply by the box, 22. Add straight down is 20. And so this remainder is the value of p of 2. That's what the remainder theorem says. Okay, if I want to do p of negative 0.5, same idea, but I don't like decimals. I prefer fractions, so I'm going to write that as a negative 1/2. Same coefficients. Let's figure that out. So that would be negative 2. Add straight down would be negative 2. Multiply by the box. 1, add straight down, negative 4. Multiply by the box, 2, and you get 0. So that means that p of negative 1/2 or p of negative 0.5 is 0. In other words, negative 1/2 is a 0 of this function. Okay, we'll talk more about that later. All right, what about something like p of I? This one's a little bit messier, but it's the same idea. We're still going to put I in the box. And as we go, we're going to simplify, keeping in mind, again, I'm going to give myself some more room here, because I know these can get a little messy. I'm going to keep in mind that I squared is negative 1, and at any step where I can do that, I'm going to simplify it. So bring down the first number, multiply by the box. 4 times I is 4i. Add straight down. 0 plus 4i is 4i. Multiply by the box. This actually isn't as bad as I thought it was going to be. Multiply by the box. 4i times I is 4i squared. Which, remember, I squared is a negative 1. So that's the same thing as negative 4. Add straight down. Negative 5 minus negative 4, or plus negative 4 is negative 9. Multiply by the box. Negative 9i. Add straight down. Negative 2 minus 9i. So that's the value of p of I. So the remainder you get from synthetic division is the same as if you just plugged that into the function. Sometimes one method is easier than another. All right, number 2 says if 2 is a 0 of p of x equals 3x squared plus kx minus 8, find k. So if 2 is a 0, that means when I plug in x equals 2, the function value should be 0. So I'm going to do this just by regular plugging in. I'm not going to use synthetic division. If I plug in x equals 2, p of 2 should be 0. So 0 equals 3 times 2 squared. Remember, we're plugging in 2 for x, not for k. So plus 2k minus 8. I just want to solve that for k. So 0 equals 12. 12 minus 8 is 4 plus 2k. If I solve for k, k is negative 2. You could also do that with synthetic division if that's your favorite thing to do. But I just did it with substitution because that was easy. All right. Number 3 says a polynomial p of x is divided by x plus 3. The quotient is x squared minus x plus 5 with a remainder of 2. I'm going to find p of x. All right, so in your book, there's a way that they talk about how to write a quotient, or how to write the answer to a division problem with a remainder as a mixed fraction. So that is kind of, I was trying to write it in words as I went. So the quotient of p of x and x plus 3 is we're dividing the two. P of x divided by x plus 3 is quotient plus remainder over divisor. The divisor is the thing that you're dividing by. Okay, so that's another way you can write that. Quotient plus remainder over divisor. Right? You have quotient over divisor. That's equal to quotient plus remainder over divisor. Another way you can write that is if you multiply both sides by the divisor, you could write it as the quotient is equal to the quotient times the divisor plus the remainder. These are two different ways that you can write this. So in the same regard, I can multiply both sides by x plus 3 and get p of x equals x plus 3 times x squared minus x plus 5 plus 2. Right? If I multiply both sides by x plus 3, that's going to cancel those x plus 3's in the denominator. And that's my p of x. Now, technically, it doesn't tell me to simplify that, but I'm going to go ahead and do that because we often want to write polynomials in standard form. So to do that, I'm going to distribute the x through the parentheses, and then I will distribute the 3 through the parentheses, and then just add that 2 on at the end. So what happens if I do that? X cubed minus x squared plus 5x, that's the red. Now the green, plus 3x squared minus 3x plus 15, and then that plus 2 at the end. Don't forget about that. If I combine like terms, x cubed plus 2x squared plus 2x plus 17. That's that polynomial p of x. So knowing this yellow theorem here, or formula, will be helpful in kind of writing the results of division when you have a remainder. Either one is fine, but make sure that you know that. All right, number 4 gives us 2 roots of this equation, x to the 4th minus 3x cubed minus 14x squared plus 12x plus 40 equals 0. So we're trying to solve a polynomial equation, and they give us a hint. They tell us 2 of the roots are x equals 2 and x equals 5. So the idea behind solving polynomial equations is if you can factor it, by all means do that. If you can factor the equation, you move everything to one side, you have 0 on the other. If you can factor it and solve it, that's great. Go ahead and do that. But if we look at something like this that has 5 terms, there's really not a known factoring method for this using traditional means. What we're going to do instead is we're going to use the hint they gave us, that x equals 2 is a 0 and so is x equals 5, or rather those are roots, to get other roots as well. So to do that, remember what we did on number 1. If x equals 2 is a 0, or rather, I guess we did this more on number 2. If x equals 2 is a 0, that means when I do synthetic division with 2, I should get a remainder of 0. So let's do synthetic division with 2. There's no missing coefficients here. Let's do synthetic division with 2 and see what we get. We should get a remainder of 0. Let's check that. So bring down the 1, multiply and add, multiply and add, multiply and add, and multiply and add. So yes, we do get a remainder of 0, which is good. More importantly than that, not only do we get a remainder of 0, we get what's called a reduced polynomial here. Okay, so if we kind of keep track of what we've done so far, if we showed that x equals 2 was a 0, that means the associated factor with that is x minus 2. If x equals a is a 0, then x minus a is a factor of that polynomial. Okay, so I know that x minus 2 is one of my factors, and that green reduced polynomial will be 1 degree lower, so it'll be an x cubed. And so we've reduced it down to that. So now what I can do is I can continue the synthetic division, because they also told me that x equals 5 is a 0. Okay, so I'm just to save some room, I'm going to go ahead and just put it right there and say, okay, if x equals 5 is a 0, let's see what that gives me. Bring down the 1. It should give me a remainder of 0. Bring down the 1. 1 times 5 is 5. Add straight down. Multiply, add, multiply, and add. Sure enough, we get a remainder of 0 again. So now I know that x minus 5 is also a factor. So x minus 2, x minus 5. And again, this is my reduced polynomial. X squared plus 4x plus 4. Okay, that's my reduced polynomial. Now, again, I'm trying to find all the roots. As you might remember from Algebra 2, we're going to expect 4 roots. And in this case, we found 2 of them, x equals 2 and x equals 5. How do I find the rest? Well, look at what's left. X squared plus 4x plus 4. Can I factor that? Yes, I can. I've got the x minus 2, the x minus 5 from earlier. That would actually be x plus 2, quantity squared. It's a perfect square trinomial. And so it says find the remaining root, so I'll just focus on that one. If I set that equal to 0, I get x equals 2 with what's called a multiplicity of 2. Remember, the multiplicity is how many times that 0 occurs. We can look at that by looking at the power on that factor. So since that has a 2 as a power, I know that that has a multiplicity of 2. Okay, and we'll talk about what that means graphically. The idea is if they give you some roots, go ahead and do synthetic division to whittle down the polynomial you're trying to find the zeros of until it's something you can factor. All right, number 5 is about graphing polynomials. Y equals x times x plus 1 times x minus 2 squared. So to graph a polynomial, I'm going to go ahead and put this over here, do it a little bit by little bit. Let's see. Okay, yeah, that should be fine. All right, so to graph a polynomial, there's a few things you need to know. First of all, you need to know what the degree is and the leading coefficient. The degree is the highest power on the x if it's in standard form. So in other words, if I were to multiply this all out, what is the highest exponent that we see? There's a trick to this, though, because if I don't want to multiply this out, and I really don't because it'd be a lot of algebra, you can just add up the multiplicities of each factor. So notice this is an x to the first, this is an x plus 1 to the first, that's x minus 2 to the second. If you add up the multiplicities on each factor, 1 plus 1 plus 2 is 4, so the degree equals 4. It's the sum of the multiplicities of each factor, or I guess I should say of each 0. So this is a 4th degree polynomial. LC, that stands for leading coefficient. That is the number in front of the x with the highest power. And if it's in factored form like this, it's still going to be this number in front of the x right here, in front of everything, which is understood to be a 1. So notice I have an even degree and a positive leading coefficient. Very briefly, I'll kind of go over all the cases. From Algebra 2, you learned that if you have, say, even, odd, positive LC, negative LC, you learn that if it's an even degree and a positive LC, that it rises on the left and rises on the right. If it's an odd degree and a positive leading coefficient, it rises on the left and falls on the right, and may do some stuff in between. Then it's the opposite for these. If it's a negative leading coefficient, it just flips everything. Falls on the left and the right if it's even, falls on the left, rises on the right if it's odd. So in this case, we have a even degree and a positive, I'll go ahead and say degree, even degree and a positive LC. So we're looking at this. It's going to rise on both sides. So that's what our end behavior is going to look like. It's going to rise on both sides of our graph. Okay, it's going to look something like that and that. Okay, so we did that. We got the end behavior. We also need to know the intercepts, and then that's just about all we need to know. The y-intercept is really easy. Just plug in 0 for x. If I plug in 0 for x, 0 times 0 plus 1 times 0 minus 2 squared is just 0, because 0 times anything is 0. So the y-intercept is at 0, so I know that on my y-axis it's going to hit at 0. To get the x-intercepts, you set it equal to 0 and solve for x. That is easy in this case because it is already factored for us. Makes graphing it a lot easier. If it's not factored, we're going to have to do the factoring or the synthetic division on our own to find those zeros. So if I set that equal to 0, that equal to 0, that equal to 0, that equal to 0, I get x equals 0, x equals negative 1, and x equals 2, which has a multiplicity of 2, because it has that power of 2 on the factor associated with it. Each of these have a multiplicity of 1. Now, if you have an odd multiplicity, it's going to cross through the x-axis at that point. So at 0 and at negative 1, we know the graph is going to cross through the x-axis there. Something you learned in Algebra 2. If you have an even multiplicity, it's going to touch or be tangent to the x-axis at that x value. And it's basically going to be, if it's odd, it's going to cross. If it's even, it's going to touch. But as the multiplicities get higher and higher, it sort of flattens out more and more at that multiplicity. And you might see that in some problems later in this course. But it's going to cross at 0 and negative 1 and touch at 2. So now we have all the pieces we need. We know it has to rise on the left and rise on the right. So I'm going to start on the left side, knowing it's going to rise. Maybe bring it a little bit closer. I'm going to end automatically on the right side, knowing it's going to rise. I'm going to be crossing through 0 and negative 1 and touching it 2. So cross, cross, touch, and sure enough, we end exactly where we should. Now, how do I know how high up it goes between, or how low down it goes between x-intercepts? I don't. I could plug in x values if that's really important to me, but to me as a teacher, it is not. So I'm not worried so much about that. I just want to make sure the end behavior is correct, the intercepts are correct, and the shape is correct. And that should be just fine. All right, number 6 is asking for the reverse. It's giving you the graph and it wants the equation. So the graph in this case looks something kind of like this. Do my best to replicate it here. Crosses at 1 and at 3 and at negative 2, has a y-intercept of 3. So it looks something like that. Okay, So we know that there are x-intercepts at -2, 1, and 3. And all of them cross. And because they don't flatten out or anything near those x-intercepts, I'm going to assume they all have a multiplicity of 1. Because they just cross and they don't flatten out or anything. So what that means is, if I have zeros at -2 and 1 and 3, that means the factors that go with that are going to be x plus 2, x minus 1, and x minus 3. Those are going to be the factors that go with it. In general, if x equals a is a 0, x minus a will be the factor that goes with it. So x minus -2, x minus 1, x minus 3. Now I left a little space there because if there's some sort of vertical stretch or shrink, we're not going to know that just from the factors. So I'm going to assume that there is some number in front, a, that could be there. It could be 1, but there's a decent chance it's not going to be 1, and we need to figure out what it is. So how do we figure out that value of a? Well, they gave us a point on the graph that wasn't one of our zeros, because notice if I try and plug in one of those zeros, it's just going to give me 0 equals 0, which doesn't help. But they do give us the y-intercept is at 0, 3. So to find that vertical stretch or shrink, plug in some point on the graph that is not a 0, and you can find out what a is. So let's plug in 0, 3. 3 equals a times 0 plus 2, 0 minus 1, 0 minus 3. 3 equals, this would be 6, actually, 6a. That means a would be a half. So when I write my function, it would be 1/2 x plus 2, x minus 1, x minus 3. So people often forget about that vertical stretch or shrink. You have to plug in a point on the graph that's not a 0 to figure out what that is. All right, number 7 is a word problem with quadratics, or polynomials. It says you have a rectangular enclosure. There is a barn on one side. Write that a little nicer. There is a barn on one side. And it says you're using 80 meters of fencing to form the other 3 sides. So let's say we've got a piece like this, a piece like this, and a piece like this. I can zoom in a different color. So we're not putting a fence along the barn side, but we are going to put it where the red is. So the red is the fencing that we're using. We're going to assume it's rectangular. All right, there's 80 meters of fencing total. So let's say that this piece is using x meters of fencing. Well, in a rectangle, the opposite sides are congruent, so this would also be x, which means this bottom side would have to be whatever's left. So notice we had 80 meters total. So far I have used 2x meters. So I would have 80 minus 2x meters left over. All right, if you add those all up, you'll see that that is 80 meters exactly. You could let the bottom side be x, but I think it would make the other 2 sides more complicated. So that's the way I'm going to set it up. All right, it says, what is the maximum area of such an enclosure? All right, well, let's find, okay, what's the area of that rectangle as a function of x? A of x, the area of the rectangle, is the length times the width, which is x times 80 minus 2x. That is the area of the rectangle. If I distribute that and kind of rewrite it in a different order, negative 2x squared plus 80x. That's an equation that gives the area of the rectangle depending on what portion x we allocate for those left and right sides. So if I let x equal 3, if I plug that in, it would tell me what the area of that rectangle would be. We want to figure out what value of x is going to make that rectangle as big as possible. The maximum area. Well, notice what this looks like, very roughly. It's a negative x squared, which means it is a parabola that opens down. And so if I'm trying to find If I'm trying to find the maximum, maybe it looks something like that, I don't know. If I'm trying to find the maximum area, notice that is just the vertex. So if it's a quadratic and it's asking for the max or the min, it's just asking for the vertex. And there are a few sort of caveats to that we'll see in our first day of class. So that's something to think about. Okay, the vertex is going to be my max or min. All right, so what's the vertex going to be? Well, negative b over 2a. Negative b over 2a. Negative 80 over negative 4 is 20. So vertex is at 20, comma, let's see, I need to know the maximum area. So if I find a of 20, I'm going to plug that in the factored form because that looks easier. 20 times 80 minus 40, that would be 20 times 40 is 800 square meters because it was in meters. So to get the maximum, I found the vertex, and you have to be careful about what it asks. So if it asks for what value of x is there a maximum, you would just say when x is 20 meters. But if it says what is the maximum area, you need to actually give what the area is. That's the y value. Okay, that's the dependent variable, 800 square meters, by plugging it back in. All right, so now the last part of chapter 2 is the more fun part because we get to use a calculator for a lot of it. Okay, so 8a says p of x is 2x to the fourth minus 3x cubed. Or actually, only part of these let us use a calculator. Never mind, we can't get too excited. 2x to the fourth minus 3x cubed minus 1. Explain how you know that the equation p of x equals 0 has at least one real root between x equals 1 and x equals 2. All right, so how are we supposed to do this? Well, there's something in your book, if you looked earlier in your textbook, there's something that in calculus is called the intermediate value theorem. I don't think they gave it this name in your textbook, but the idea behind it is this. If you have what's called a continuous function, and a polynomial is a continuous function, because when you draw it, you can draw it without having to lift your pencil. Okay, if you have a polynomial function, and so I'll just draw something like this. So let's say I have a polynomial function and part of it looks like that. All right, what this intermediate value theorem says is if you have two x values a and b with corresponding y values f of a and f of b, if f of a and f of b have opposite signs, there must be at least one 0 on the interval a, b inclusive. This is something called the intermediate value theorem that you're going to study a lot more in calculus next year, but it is important for now too. Okay. So if basically if you plug in two different x values and they have opposite signs, there's got to be a 0 between them. Now this, for our cases, we're going to say this only works for polynomials. There's other ones it works for as well, but for us, we're going to say it only works for polynomials. You can't just do it for anything. So if I have a polynomial function, and I plug in two different x values and they have different signs for their y values, there has to be a 0 between them. You can kind of see that in the picture, right? Notice that f of a is positive, it's above the x-axis. F of b is negative, it's below. So there has to be a 0, at least one 0 between them. So for 8a, let's just find p of 1 and p of 2 and hopefully find that they have different signs. P of 1 is 2 minus 3 minus 1. That is negative 2. It's less than 0. So p of 1 is below the x-axis. Or I guess I should say the point 1 comma p of 1 is below the x-axis. Okay, what about p of 2? P of 2, if I plug that in, that is 2 times 2 to the fourth is 32 minus 24 minus 1, which is 7. believe, yep, 7, which is greater than 0. So notice that one of them is less than 0. One of them is greater than 0. They have opposite signs. So because P of 1 is less than 0 and P of 2 is greater than 0, there must be at least one real 0. Handwriting's getting sloppy. There must be, it's not much better, at least one real root between those two, or at least one real 0. Okay, so that's something called the intermediate value theorem. You'll see it a little bit more in calculus next year. Now part B says, okay, actually what is that root? And it lets you use a calculator. And the reason it does that is because there's really not a way to find it. There's really not a way to find it by hand. So if I want to find this root, I'm going to go to my graphing calculator. I went ahead and opened a graphs page. So as a reminder, when you turn on your calculator and you get to this home page, you can say new document, option 1. I'm going to say no because I already have one open. If you don't, it'll just bring up this. And I'm going to add a graphs page, option 2. And then where it says f1 of x, I'm going to type my function, which is 2x to the 4th minus 3x cubed. Kind of look at how it's lighting things up on the left side in red in case you need to see what I'm pressing. Minus 1. And when I graph this, I get this polynomial function, and I want to find where it crosses the x-axis. I want to find the zeros, or the roots. So to do that, I go to Menu, Analyze Graph, so that's option 6. I'm trying to find the zeros. I'm trying to see where it crosses the x-axis, so that's 0. So Menu, Analyze Graph, 0, option 1. It says, okay, lower bound. So when it says this, you're going to go a little bit to the, so let's look at this first 0 over here. I'm going to go a little bit to the left of the 0 and hit enter. When it says upper bound, I'm going to go use the trackpad to go a little bit to the right, hit enter, and it gives you that 0 right there, negative 0.618. And since your book says to round to the nearest tenth, we'll say negative 0.6. All right, what about the other one? Menu, 6, in this case 0, so option 1. Go a little bit to the left of it, hit enter. Go a little bit to the right of it, hit enter. You can see it's about 1.62, or if we round to the nearest tenth, about 1.6. So you can use your calculator to find that. If you know the solve function, you can use that as well, whatever you're more comfortable with. So negative 0.6 and 1.6. It's about what those are. Not exactly, but about what they are. All right, number 9, solving a polynomial equation. This time we're not going to use our calculator. We can kind of put that away. All right, when you're solving a polynomial equation, move everything to one side. Zero on the other side. And if possible, you want to factor it. And in this case, it has 4 terms, so it might be a good idea to try factoring by grouping. So remember, to factor by grouping, you look at the first 2, take out a GCF from those. So for example, I can take out an x squared here, leaving me with a 2x minus 3. Then you look at the next 2 and you take out a GCF. From those 2, I can take out a negative 3, leaving me with a 2x minus 3. Notice those signs changed inside because I took out a negative. So be careful of that. Now if I look at this, there is a greatest common factor of 2x minus 3. It's common to both. Remember, if these are the same, that's going to be one of your factors because it's a GCF. If it's not the same, you can't factor by grouping and you have to try something else. If it is the same, I have those 2, and then what's left when I take out that GCF is an x squared minus 3. Long story short, everything inside the parentheses is one factor, everything outside is the other when you're doing factoring by grouping. All right, now just set each of those equal to 0 and solve for x. 2x minus 3 equals 0, x squared minus 3 equals 0. gives me x equals 3/2 is one of my answers. Over here, I get x squared equals 3. Square root both sides. Don't forget you need a plus or minus, so plus or minus square root of 3. So there are 3 zeros as we'd expect because this is a third degree polynomial that we're finding the zeros of, or the roots, or the solutions, x-intercepts, all synonymous. Okay, so if you're able to factor, absolutely do that. If you're not, like on number 10, you have to do something different. 3x to the 4th minus x cubed plus 4x squared minus 2x minus 4 equals 0. All right, this I cannot factor. There are too many terms. I can't factor by grouping. I don't know a factoring method for this. Maybe you're smarter than I am, and you know a factoring method, but I do not know a traditional factoring method for this. I need to use synthetic division. The problem is, unlike one of the ones we did earlier, unlike number 4, where they gave us some hints to get us started, there are no hints here. So what am I supposed to do? Well, I can build a list of possible rational zeros. Possible rational zeros. If I have nowhere to start, this is all the factors of the last term over all the factors of the first term. We usually call that P over Q. It's all the factors of the last term over all the factors of that leading coefficient. So, okay, what are all the factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4. Over all the factors of the leading coefficient, plus or minus 1, plus or minus 3. If I kind of separate this into individual fractions, I've got, okay, 1 over 1, 2 over 1, 4 over 1. If I do it over 3, 1/3, 2/3, 4/3. So if I'm taking into account the plus or minus, I've got 2, 4, 6, 8, 10, 12 possible rational zeros. Now before I move on, I want to kind of clarify. These are possible rational zeros. That does not mean that every zero we get is going to be in this list. But what it does tell us is if we have a rational zero, it will be in this list. Remember, a rational number is a ratio of 2 integers. But if we get something like square root of 2 as a 0, it's not going to pop up in this list. But if there are rational zeros, they will be in this list. The idea is we're just going to go through synthetic division until we hit something in this list, and then we're going to see if we can factor it from there maybe. And if not, we'll just keep doing synthetic division. So let's start with synthetic division with positive 1, hope for the best. And I have a good feeling about this one. I feel like it's going to work out. It has nothing to do with the answer key in front of me. I just have a good feeling about it. So let's give it a shot. Let's do some synthetic division here. Bring down the 3. 3 times 1 is 3. Add straight down, that's 2. Multiply and add. Multiply and add. Multiply and add. Oh, that was a very lucky guess, right? Starting at 1 was a good idea. That is one of our zeros. So I'm going to kind of keep a list over here. X equals 1 is one of our zeros. Now look at what's left. That is our reduced polynomial. So we already know we've got that x minus 1 factor there. This is my reduced polynomial, 3x cubed plus 2x squared plus 6x plus 4. Remember, that reduced polynomial is going to be 1 degree lower than it was before. So a 4th degree becomes a 3rd degree. That you can factor by grouping. Could you go ahead and do synthetic division again? Sure. Once you get down to a quadratic, though, you never ever want to do synthetic division because there is no guarantee you're going to have a rational zero there. There's really no guarantee you're going to have a rational zero in general, but if you're given a test, you should expect at least one rational zero. But when you get to a quadratic, to an x squared, you should start factoring or completing the square or quadratic formula, but don't do synthetic division at that point. Here you have a choice, but I'm going to factor by grouping because that's easier, and it turns out it works. Out of these two, I can take out an x squared as a GCF, leaving me with a 3x plus 2. Out of these two, I can take out a 2 as a GCF, leaving me with a 3x plus 2. Because that factor is common to both, I'm going to have an x squared plus 2 as one factor and a 3x plus 2 as another. And look, beautifully, it factored all the way down. Okay, since I went ahead and carried that x minus 1 factor, I'll erase that, and I'll go ahead and solve this. Set each of these equal to 0, x equals 1. This one, x squared plus 2 equals 0. This one, x equals negative 2/3. So I solved the first and third ones because I could just do it in my head. This middle one, if I move the 2 over, I square root both sides. Be careful here. First of all, square root of a negative means I'm going to have an imaginary solution. And it does say find all real and imaginary roots, so I do want to include this one. So let's see. This would be x equals, I pull out the negative as an I. I need to remember a plus or minus because I square rooted both sides, so plus or minus I, and square root of 2 doesn't simplify. So look, I have 1, 2, 3, 4 with the plus or minus solutions. Okay, and it's a 4th degree polynomial, so that's what I expect. All right, so that's that. Number 11, I'm not going to spend a lot of time on. All I'll say is you can think about what we've done. It doesn't need to be a full paragraph or two, maybe just a couple sentences. It explains how you can solve equations using your calculator and how you can do them by hand, right? We talked about factoring by grouping. We talked about looking at possible rational zeros. We talked about using the solve function, graphing on your calculator. You can do this on your own. So I'm going to put a little smiley face because I bet you can do it on your own. All right, number 12 says, find the sum and the product of the roots of that polynomial. Okay, now you could just find the roots and find out what they are, but there's also something in your book. I'm going to try and find it here. There's a theorem in your book that tells you how to find the sum and product of the roots. It's on page 86. It's theorem 5. Probably didn't look at this in algebra 2, but it's sometimes can be handy. And it basically says if you have a polynomial, it gives you a way of finding the sum and the product of the roots. The sum of the roots is negative a sub n minus 1 over a n. That's the second to last, or I'll say the second coefficient, well, the negative in front. The negative of the second coefficient over the leading coefficient. It's basically what it's saying if you look at the theorem. It's the negative of the second coefficient over the leading coefficient. The product of the roots is kind of a piecewise function. It's either the constant term over the leading coefficient, if n is even. So that's constant over leading coefficient. Or if n is odd, it's the negative of that. How do you prove this? I don't know. It's probably really fun. Or it's really awful. It's one of the two. But it's just a result that's shown in your book. So if n is odd, it's the negative of that. It's the negative of the constant term over the leading coefficient. So instead of actually finding the roots, I'm just going to find the sum and product using this. So in our case, our p of x, if you want to think of it that way, our polynomial is 2x cubed minus 5x squared minus x plus 8 equals 0. So the sum, as we see up above, is equal to the negative of the second coefficient over the leading coefficient. So negative 5 over 2 is 5 halves. So whatever the roots are, they add to 5 halves. And the product, remember, so n in this case is the degree. This is a third degree, so n is odd. Looking at this second possibility here. It's the negative of the constant term over the leading coefficient. So the negative of 8 over 2 is negative 4. So whatever the roots are, they definitely multiply to negative 4. So this is something, again, on page 86, theorem 5. To be honest, we probably won't use this very often this year, but it's a good practice to be able to look at a kind of a abstract theorem and figure it out what it's saying without having to necessarily do an example or a litany of examples before that. Should hopefully help. All right, number 13 says find a cubic equation with integral coefficients and roots of 3i and negative 5. Integral coefficients means everything is an integer. All the coefficients are integers. We need a cubic equation. So cubic equation means we're looking for an x cubed when we multiply everything out. All right, so as I said earlier, if x equals a is a root, x minus a is the factor that goes with that. So for example, if negative 5 is a root, x minus negative 5, x plus 5 is the factor that goes with it. Okay, x plus 5. If x equals 3i is a root, then x minus 3i is the factor that goes with that. Now, there is a theorem from Algebra 2, and in your book you could have looked at here earlier, that says if you have a polynomial equation with rational coefficients, if a complex number is a 0, its conjugate will also always be a 0. So if a plus bi is a 0, we always expect a minus bi to be a 0 as well in general. So in this case, if 3i is a 0, we expect negative 3i to be a 0 as well. So the factor would be x plus 3i. Complex zeros occur in conjugate pairs. Okay? Complex zeros occur in conjugate pairs. It's called the fundamental theorem of algebra. It's a consequence of that. I'm leaving a blank in the front because we need to have integer coefficients, and so I'm going to multiply by something to clear out any fractions if I need to, but in this case I don't think I'll need to. So I'm going to go ahead and FOIL this out. I'm going to look at these two first. When I FOIL those out, I get x squared plus 3ix minus 3ix minus 9i squared. Notice the imaginary units will cancel. Remember that I squared is negative 1, so this becomes x squared plus 9. And if I FOIL that out, I would get x cubed plus 5x squared plus 9x plus 45. And we need integer coefficients, and that's what we have. But if I didn't, let's say I had a 1/3 in there somewhere, I could just multiply by 3. And although we don't want to do that in most cases, it's not going to change the fact that the zeros are what they are. 3i, negative 3i, and negative 5. So it's okay to just multiply that through because it won't change the zeros if we need to have integer coefficients. But here I didn't have to do that. So I set it up. Given their zeros, I put a factor for each one, keeping in mind that if a plus bi is a 0, so will a minus bi. Again, as long as you have rational coefficients. So just keep that in mind. All right, last one. Number 14. P of x is a cubic polynomial with real coefficients. Explain why an imaginary number cannot be a double root of a given equation. Well, let's think about it. This we're going to kind of do like a proof by contradiction. So let's suppose that x equals a plus bi is a double root. Okay, if x equals a plus bi is a double root, that means it occurs twice. So if I kind of keep track of my zeros, I know that a plus bi is one root, and because it's a double root, it's got to be another one. But remember, if there are real coefficients, I think I was saying rational earlier, but they just have to be real. If there are real coefficients, anytime a plus bi is a root, its conjugate has to be a root as well. So for this one, if a plus bi is a root, I know that a minus bi has to be a root as well. And then for this one, if a plus bi is a root, again, for that one, I also need a minus bi to be a root as well. I'm doing this very generally. You could put numbers to this if you want. But notice there have to be then at least 4 zeros. I'm not including whatever other zeros there might be. Problem with that is if it's a cubic polynomial, the fundamental theorem of algebra tells us cubic polynomial, in which case n equals 3, should have exactly 3 zeros. No more. This one has 4, so that's a contradiction. contradiction, a cubic polynomial cannot have an imaginary double root. Because that would give it too many zeros. Okay, could a fourth degree polynomial? Maybe, right? But not a cubic polynomial. So hopefully you enjoyed that very long, thrilling movie of all of the work for chapters 1 and 2 test. Hopefully this is beneficial to you as you're looking at some of these problems. If there are problems you're still having issues with, please come see me, ask questions, and I will straighten them out for you. But I hope you have a wonderful day.